Well, as we roll into this, thank you for all your assignments. Everyone got them in. I was just mentioning earlier. I was quite surprised. I logged on, maybe it was actually in the afternoon at noon on Sunday, and there were 10 or 15, I suppose. So I was surprised to wake up at yesterday morning by the snow, of course, but also to have them all there, which is great. And they all arrived on the day. And so that's fine. It was only useful to me because I wanted to actually do something with them. So I guess I'm a little bit not disappointed, but I think the course has kind of evolved into something interesting, perhaps more than I wanted, because it's getting quite complicated in terms of deliverables. So the right-hand side, I guess, is what you see the different weights are. So these are trivial presentations, so these will be things to do with quizzes. 219, at the time when we had this class before, students were tasked with making videos to follow the lectures, and they did a so-so job, but those are there available. The ones last year were quite good, I think, were more substantial, and those are now online. The participation credits these days are by the things that you sent me. And those are, I guess you won't see it like this, but those are all online. There'll be one that's open now. These are, participation is right here, I guess. You uploaded your file already, and I guess the one that's open today is this. You don't have to worry about this because you're physically here. We have to figure out a way to get names on a sheet in alphabetical order so I can put you in instead of you doing the stuff that's online, because that's the deal. And so that's kind of what we're doing now. So I guess I should probably note that these assignments are, I guess, so you don't need to do those. So what I will do is I'll upload 10 points per person for each of those, for those people who are come. So people can do it any way they want. If they don't want to get together in the room, it's a great room actually, decent size. Lots of social distancing there. Everyone. And so, yeah, fine. So it's actually quite a pleasant room, except for being across campus. So they're all online. You'll see that some of them, I messed up on the hot links, and some of them, I think, some of you have automatically compensated for that, as I heard today, and some of you went with the hot links, which were given, and so I ended up with some things, double things for 2 of the assignments, and then had to fill in things myself, God forbid, and so that doesn't really, you won't have to worry too much about that because you will be here. But if you choose not to participate, then that is your prerogative to do it the other way around. So I guess, as I said before, I'm a little bit disappointed in myself because it's just kind of complicated. There's, do this quiz here, this quiz there. But I think the quizzes are relatively trivial for these 2019 and 2021 assignments because they're quite short. The ones are more substantial for the in lieu of class because those are the full 75-minute periods in general. And then your other deliverable for 30% of your grade is to make a presentation of your choice and to then view everyone else's presentations of their choices, and that caps it out. So no exams. So this is kind of a pleasant class. I think it's kind of a little bit of a romp through geothermal energy. It's kind of devoid of these incessant evaluations. Of course, there are incessant evaluations, but they're really not very difficult. And so I think hopefully you're stretched by the interesting material. So that'll be my prerogative my challenge, I suppose, to get it up. How are we going to take attendance in class? Do you all know each other? Don't? You're all engineers, right? You're not a single cohort moving through it? Don't know anybody? Don't talk to each other? Certainly don't talk to the professor. I know this, Christ. So, well, think about it and you can figure out tell me how to do this. I mean, I can go around the class and take people's names. I don't want to touch anything you give me, of course, in this day and age. And you probably don't want to touch it yourself, or maybe you don't care. So figure out exactly what's going on, okay? All right, so that's anything we need to talk about in terms of the mechanics of the class. I think it's pretty straightforward. It's kind of complicated, but I don't think it's anything that's beyond you. What else? So if you are engine engineers, you probably, since I'm the only guy who's taught 303 in the last decade and a half, then you probably took it from me. And so we always like to start things with something interesting. And of course, what we'll talk about today is heat flow, because geothermal energy, of course, that's kind of annoying. That's better. Geothermal energy relies on heat flow in the crust, geo as in the earth, and thermal as in heat. Both Greek words, I guess. Certainly geo is, and thermos must be as well. And so the mechanics of how the world works is an intrinsic component of that. And so we just happen to have quite a stark example of Mother Nature doing what she wants to. And I haven't looked at all of these. These are kind of befores and afters of what's been going on in Tonga. Tonga's, of course, halfway around the world. I was looking earlier on, and we don't really want to, a lot of it will be ashfall. I guess this is kind of interesting, yeah. So this is what it looked like as it was developing. This is pre-eruption. There was some kind of failure that occurred, perhaps slipping into the sea. If you slip a big pile of material into the sea that was sitting there, like having a weight on top of a bottle, you take the weight off, then the bottle can pop. I mean, not a perfect analog, but basically you uncork it. And there was a huge explosion that put ash clouds, I think, up to 10 miles into the 20 miles into the air. So a mile is about 5,000 feet, right? So it was about 100,000 feet, 20 miles, I guess. And then left merely the remnants of something that was originally there. There's another interesting, if this opens, it's a bit slow. That's not a singular event. These happen actually quite often. I'm not sure if, yeah, it is opening, just taking a long time to open PowerPoint. And if I bring this up, seems very slow doing all these things, but it's getting there. Then I can think of this. So this was 2 years ago, almost, well, it was December 2018. So I guess we're in 2019 now. So yeah, it's 3 years ago, I guess. And this was Anak Krakatoa. If you have ever heard of Krakatoa, Simon Winchester had an interesting storybook about Krakatoa. The shot heard around, the blast heard around the world, so loud it was. And it was a volcano that existed in Indonesia that basically destroyed itself by a collapse, a huge collapse and eruption in the 1800s, I think. And Anak Krakatoa is something that grew up in its stead. Anak must mean son of in whatever dialect is spoken in Indonesia. And 3 years ago, there was a big collapse that occurred that looked like, it's relatively small here. This is the original Krakatoa volcano, which 150 years ago could be heard everywhere around the world. And actually this eruption on, what was it, 2 days ago, a few days ago, in Toga, was heard in the UK. And you can do the calculations at 300 meters a second for the speed of sound in air. And it comes out to be the exact timing of the explosion and eruption. But this one in 3 years ago was a volcano that was growing. It collapsed. And so it looked like this, certainly not as big as the one in Tonga. I said Toba, not Tonga. that collapsed, slipped into the ocean, and as a result of that collapse, if I do this, see if it'll work. This is it right here in the middle. You see this here. So this is just a model of exactly what happens. So the side drops off it. It's worse than an earthquake. At least on an earthquake, the sound waves travel through the earth. It's faster than the speed of a tsunami or the speed of sound in air. And so you get some forewarning of a tsunami because the earthquake has occurred and you know it. But if it slips silently into the ocean in terms of a landslide, you have no forewarning. And so this was a particular example in Indonesia. Again, this is a model, but it shows the waves emanating from a big brick going into the water. And it killed a number of people who were having a party. And of course, the tsunami isn't some kind of huge breaking wave that comes over the shore, but it's kind of an inexorable rise in sea level, which never goes down again and washes everything inland. And so geoscience in action is kind of what we'll draw on for what we'll talk about today. And so what I was going to do today is talk about geothermal energy. And I guess I will use my pad as I want to. Okay. And I guess I was going to use this, so I will use this. See if I can't remember exactly what it is, but it's probably something that I did look at it quickly. See if it is able to link. Probably explains things a bit better than me, if you can imagine that. You're allowed to laugh.
In 1977, two scientists published the most complete picture of the ocean floor that had ever been created, revolutionizing our understanding of the Earth. Named the Tharpism Map after its collaborators, this illustration was produced using sonar and measurements of the water's depth. It revealed, for the first time, a complex network of underwater mountains and ridges, and provided key evidence that supported the emerging geological theory of plate tectonics. This theory states that the Earth's solid outer shell, the lithosphere, is broken into plates. These plates shift and slide over the asthenosphere, the molten upper portion of the mantle. Oceanic and continental plates meet and interact at boundaries that crisscross our planet. Because 71% of the Earth is covered with water, the majority of boundaries are found on the seafloor. When two oceanic plates tear apart from each other at a divergent plate boundary, the space between the divergent plates fills with magma that hardens when exposed to cold seawater. Over millions of years, this process has built chains of underwater volcanoes and rift valleys called the mid-ocean ridge.
When the plates move apart, they rip open the Earth. The mid-ocean ridge, which runs around our planet like the seam on a baseball, is where the Earth creates its outer skin. And as these plates move, they're in a synchronized ballet.
There are few places on Earth where the mid-oceanic ridge rises out of the ocean, giving us a chance to see this phenomenon on dry land. Iceland is one of them. The island of Iceland was once an underwater section of the mid-ocean ridge. Over millions of years, it was pushed up above sea level by a giant volcanic hotspot. Here, we can see a divergent plate boundary, a stretch of the mid-Atlantic ridge where the North American and Eurasian plates are spreading or rifting apart. Geologist and oceanographer Dr. Bob Ballard has come to this unique spot where crystal clear glacier water has filled a section of the mid-ocean ridge that has been raised above sea level.
Boy, that's truly amazing. I'm literally at the boundary of creation in Iceland. On my left is the North American plate right here. I can put my hand on North America. I can reach over here and put my hand on the Eurasian plate. And this is the very spot where the Earth is spreading open, about an inch a year. about your height in your lifetime.
When two plates are spreading apart in one section of the world, other plates are moving toward each other in a different area, forming a convergent plate boundary. At these kinds of plate boundaries, one plate can slide underneath the other in a process called subduction. Or the two plates can crash into each other, creating a mountain range. The Himalayan mountains formed this way when two continental plates collided. On the Mediterranean island of Cyprus, we find an example of a convergent plate boundary that was raised above sea level 90 million years ago as the African and Eurasian plates collided. Dr. Ballard has come to explore this unique part of the mid-ocean ridge in the light of day.
I'm standing on what was an ancient ocean floor, would have been thousands of feet beneath the sea. And what we're looking at is an area where the subsequent collision of these great plates, the African plate and the Eurasian plate, then began to force this part of the ocean floor up to where it is today.
This upward movement revealed ancient volcanic activity that had taken place on the ocean floor.
If you look into that upper section, you'll see these round-looking objects, and those are actually what we call the pillow lavas, because as the lava comes out, and no sooner does it come out, it's quenched. And then it expands and continues to quench and forms these pillow-shaped forms, and then it'll pop out, form another one, pop out, form another one. So you can literally see all these different areas in which the molten lava actually expanded out and then cooled.
The study of plate tectonics, from the tallest mountains to the bottom of the ocean, helps scientists understand the extraordinary processes that continually shape and reshape our planet, sculpting majestic landscapes, causing earthquakes and volcanoes, and supplying natural resources.
Like heat, for instance, I guess. The end? Yeah, I think that's it. Good. All right. Well, that's probably a better job than I could have done, so that's good. That puts kind of sets the scene for us. Interesting features of that. Of course, Bob Ballard, in terms of the people involved, Bob Ballard, I guess, was an ocean explorer in the 1950s, and the CIA decided to build him a boat called the Glomer Challenger. And the Glomer Challenger was the boat that went around looking for whatever the name of the Russian submarine was that was lost in the Pacific that the Russians couldn't find, but they ultimately found. So a big open bottom in it, so they could actually lift up the submarine into the belly of the boat underneath. And it was billed as an ocean exploration activity. It certainly wasn't billed as a CIA looking for Russian submarines. And I guess I'm not sure whether they got nuclear warheads or code books or whatever it was, but it was a kind of an interesting component. And of course, that, I suppose, in some respects, would have been the beginning of the ocean drilling program, which has been what has defined whether plate tectonics is real or not. You know, the real evidence for plate tectonics. Tectonics was originally described by Alfred Wegener, maybe in the 1920s, with the idea that both the west coast of Africa and the east coast of South America, they kind of looked like they fit. But there was no evidence to say that, except until the ages of spreading centers in the middle of these divergent boundaries within the middle of the Atlantic Ocean were sampled by drilling. And it's actually not the materials themselves, it's the fact that they have alternating polarities. So the Earth's magnetic field switches polarity every, many thousands or millions of years, and that polarity gets recorded in the rocks, which are erupted then and solidify. And so as you go out from the mid-Atlantic rifts, they change polarity from north-south to south-north, etc., as you go across. So that was the evidence that sealed the deal. Not just a theory anymore, but something that actually had mounting evidence to be able to explain what's going on. So that's kind of what we will look at. So our interest is in understanding how the Earth works, to be able to understand exactly where we might go to be able to prospect for heat. We've kind of alluded to where you might go. We talked about plate boundaries before, I guess, the last couple of sessions, and where we might not want to go for heat. And we might want to know whether that heat is sustainable. Can we use it and it will be replenished? Or is it a source that we are going to roughly deplete at the same rate at which it's being created? And so those are some questions that we might want to ask ourselves. And so to be able to get some idea of that, if I can do this is all my favorite thing, as you know, is maybe to talk about where we're coming from before we actually step out in our next step. And we talked last time about kind of the big picture of energy in the world and in the US. We noted that the US uses about 20% of the power, the energy, with 5% of the population. That's just the way it is in developed countries. Good numbers to keep in your mind. The US energy usage, 100 quads. The world energy usage is about 500 quads per year. And that corresponds to exajoules. I always have to look it up, but exajoules is kilo, mega, giga, tera, peta, exa. So it's 10 to the 18. So this is 10 to the 18 joules. And roughly the same in terms of trillion cubic feet of natural gas. They all work out to be roughly the same number. So some numbers to start keeping in your thoughts. So in terms of the reservoirs that are available to be able to supply those, we talked about gas hydrates, huge reservoir. The only reservoir that gets smaller as time goes on because these are formed offshore, and the assumption is that they exist everywhere where they can exist, but they don't necessarily exist at the maximum saturations there. So these would be 1 million exajoules. And so if you need 500 per year to keep the world alive, that I guess 2 times 500 would be 1,000. So that would be 2,000 years worth, right, of that order. Similarly, the geothermal resource in the US, we talked about hydrothermal resources. So those are the ones that are present at the plate boundaries. And we'll talk about that in due course. But 10 to the 4 exajoules, so that's what, 10,000? So that would be 20 years worth of energy. Is it replenished, or is it actually depleted when you use it? I guess that's something we can talk about and try and understand a little bit about. And the other reservoir is the deep geothermal energy that exists beneath our feet. I think this is an estimation down to 10 kilometers. It's not all recoverable, but it's there. So if you could recover it, this is the kind of reserve you'd had, which is 10 times the hydrate reserve. So this would be 10 million. So I guess that would be 20,000 years worth of power for the world within the US alone. And so what we'd like to be able to do is understand, where does this reserve come from? How quickly is it replenished? If we recover it quickly, will it outstrip the rate of replenishment? And try and understand exactly the kind of big picture. So I think of this class as kind of a conversational class because you can see all the stuff online. We kind of do follow the two texts, Bill Glassley's book and I don't know. I'm trying to think what the name of the other text is. Bixley. Why is it AG? I'm trying to think. I thought it's Grant and Bixley. I guess I'm not sure why I call it AG, but it's Grant and Bixley. I won't talk about these. These are just some linkages. Oh, the other thing I didn't mention, but of course you know this because you were listening last time, is that all these materials are available to you on the course resources page. And so if you haven't downloaded these because you didn't know you could, then the notes all exist here. These are, I was going to had great intentions to change it from last semester, but I didn't quite get around to it. So this is what we're looking at today. So you'll recognize that. And so you have access to those if you want. So this is kind of the motivation. So we're interested in all of these resources, especially I'm interested in this one. I spent 30 years of my life being interested in EGS, geothermal energy. Still working on making it viable. It's just very expensive to recover, and we'll see why that is as we go through this class. But we can think about the resources in these different environments that we touched on briefly on Thursday. And that is, we can look at a spectrum of different reservoirs. I suppose, actually, from almost thinking about it, I don't know why it doesn't make a straight line sometimes, from maybe optimal to less optimal. And so I say that because we made the case that, I guess we talked about it. We made the case that, I think I used H, right? The heat rate that you can recover is equal to the volumetric flow rate times the density of the fluid times the specific heat capacity times the temperature differential. So if you want to have a successful geothermal plant, H dot is the heat rate. This is power. You want to have three things. You want to have a mass flow rate which is big, right? You want to have this big, obviously. You want all of these things individually or collectively to be big. Can't be that one of them is missing. For instance, if you can't flow any fluid through your reservoir, and this is zero, doesn't matter how hot it might be or what the specific heat capacity of the fluid might be. This is usually the specific heat capacity of water, 4.1 kilojoules per kilogram per degree centigrade. And so if one of these is missing, it completely kills the system. And so you have to have all of these present. And so this one's a no-brainer. If you have fluid in it and that fluid is water, then you have that. You can tick that off. But what you want is both temperature and mass flow rate. Certainly, if you look at the Earth's crust, as we will, we know that the thermal gradient, and we'll see why that is soon, varies between a low thermal gradient in the middle of the continents, which is maybe about 25 centigrade per kilometer. And at plate boundaries, it's optimally as large as 50 centigrade per kilometers. So we said last time, if you go down 4 kilometers, and it's 50 centigrade per kilometer, that's 200 degrees centigrade plus whatever the surface temperature is, a small amount, but it's 200 degrees. So you almost certainly have heat at some depth. If it was only 25 degrees centigrade per kilometer, at 4 kilometers, you'd have 100 degrees centigrade. Still hot enough to boil water at atmospheric pressure. But what you might not have is the ability to recover it in terms of heated fluids. And so that's why I make this point that it's optimal that if you look at, say, the geysers in California on the plate boundary, then because deformation is occurring all the time, then the rock is broken up and it has a high permeability. If you have a high permeability, you can get a lot of native fluids out of them and re-inject the cooled water after you've used it to generate power. If you're in sedimentary basins, such as, well, shales aren't probably a good example, but if you look at the Gulf of Mexico or if you look at Oklahoma, where the reservoirs might be quite warm, petroleum reservoirs, hydrocarbon reservoirs, then the produced fluids that you bring out of there, the oil, if it's hot, you could use to scavenge the heat from it. The water, if you bring it, all you can do is scavenge heat from it because it's no use otherwise. And then you might be able to recover some energy from that. And if they're already permeable enough to be able to get hydrocarbons out, then they're probably good enough to get water out in sufficient quantities. It's just that you're probably not interested in the water so much because the value of a barrel of oil is 50, 60, 70, probably $80 now, as I haven't followed it lately. And the barrel of water at 200 centigrade is probably worth a quarter of a dollar. And so the relative values of these are very different. Of course, if you want to go beneath your feet where we are, probably the thermal gradient beneath us is at the low end. We're in the middle of a continent. And if you do get down 4 kilometers, it may be 100 or 110 degrees centigrade, but you might not have very high flow rate. You have to make the reservoir. So the concept of EGS is that you have to physically make the reservoir, like this little cameo on the right-hand side. You drill a hole down that you're injecting cold water. You hydrofrack it, basically, or you hydroshear it in a certain way, subtle differences between them. You make a connection between somewhere, you make a reservoir that is now permeable, that doesn't have much water in it, but then you drill another hole down, and then you use that to circulate cold water in across the reservoir, heat it up, recover it to the surface, generate electricity, and then re-inject the cold water. And so the reasons why we're interested in this is because we want to have each of these things. We're almost guaranteed that we have temperature, but we're not necessarily guaranteed that, one, we have water in place. Sometimes that's not a problem because you can put water in. And secondly, that if we have water in place, we can get a big enough throughput of that water to be able to scavenge heat like a big geological radiator in the subsurface. And so that's kind of where we're coming from to look at this. So it would behoove us to know something about the origin of the geothermal gradient. Why does it look like this, that increases with depth? Why isn't it backwards or whatever? Why does it change in given locations? And what is the rationale for that? And I suppose you could also ask your question, what's the rate of heat supply? And is it enough to be able to supply, for instance, this 500 exajoules that we use per year, which is equivalent, we said last time, is something like 10 to 15 terawatts. So energy is exajoules. Energy per unit time is watts. And so something like 15 terawatts. So tera would be 10 to the 15. Right? If you're not up on your Roman classifications. And whether the amount that we would use to be able to replace this 15 terawatts with geothermal energy, then it has to be replenished at a similar amount or a similar rate. Otherwise, it's not sustainable, right? And so what are the relative order of magnitudes of this? I'm trying to think why I had all these little commentaries here. I guess I was trying to get people to use those in their thought process for this, but don't ignore those. So, the Earth. One planet out of many surrounding us. I think our universe is 13 billion years old, something of that order. I think the Earth is something of the order of 4.3 billion years old. 4.3 billion years ago, it would have been a glob completely molten. It was hit by a meteorite, which is what people believe carved off the moon. So an impact blew off the blob of stuff that was the size of the moon, which was kept in orbit around the Earth. And at that time, it would have been around the genesis of the Earth, I suppose, sometime after 4.3 billion years, not within a billion years, the moon was carved off. And both bodies were just molten rock that were doing their thing and presumably cooling or heating with time. And probably mainly cooling. So the idea is that originally, 4.3 billion years ago, this would just have been a blob of molten minerals. After time, it spherically differentiated. So that means that if you can imagine an ice cube as an analog, you heat the outside of the ice cube, it melts. This is the opposite. The atmosphere in space is a vacuum and very cold. This is hot, so it cools off to the surface. So physically what happens is it cools from the outside. As it cools, the individual homogeneous mixture of what is present with all the molten minerals together, homogeneously distributed throughout the melt, they start to differentiate. As they cool, some become more dense and some become less dense. Those that become more dense, like the iron core, will sink with gravity to the center of the Earth. And those that are more buoyant and less dense will float to the top and do what they do. And so if you look at the generation of that through the years, then you start off with something that's completely molten, and slowly with time you start to accrete a core, and the core is the most dense material. It's almost solid iron. The solid portion of the core is solid, but outside there's molten iron, which is in motion like a fluid. And then above that, there's the mantle, which is rock as we know it, as you'd see coming out of volcanoes, etc., and lava flows. And then just this thin, skinniest rim on the top of where we sit is something that's probably of the order of 70 kilometers deep at its deepest. The deepest drill holes might be about 10 kilometers that you can drill into this thin veneer on top of us. And in addition to this, the differentiation of the crust that occurs ends up creating these plates on the surface, but it also has an active system of heat transfer from the very hot core to the outside rim that has to do this in the way that's most efficient to be able to do that. And some of this is by conduction, but a much more efficient way of moving heat from the core to the exterior is by convection. And so both of those components operate. And so you can read these statistics for yourself. Radius of the Earth, 6,400 kilometers. The solid core is 1,000 plus kilometers. It's molten to 3,500 kilometers. Temperatures are relatively hot. It's differentiated by density, as we've talked about. And then above this, there's two components that we're interested in, a lower and upper mantle. We're not interested in the molten core, it's too far away. And that is liquid, but it's highly viscous. And I don't know, well, I think there's some notes on what the viscosities are later on. And as I said before, the plates that we sit on at their deepest are something like 70 kilometers. They're somewhat less than that in some parts. And in terms of the heat supply, well, we're still losing heat from this central core from the initial formation of the Earth by impacts at the beginning of its accretion at the beginning of the universe. And so 40% is taken by heat supply from this rigid core, and 60% being driven by radioactive decay, which generates heat as it decays. And so most of those elements are radioactive elements, uranium and thorium, some potassium. These are just heat production rates per unit mass, watts per kilogram. I'm not sure you need to know these, but all that's interesting in these is that the strongly radioactive ones are quite large. Potassium is 3 orders of magnitude less in terms of the productivity. And so we end up with a picture like this. So not only does it differentiate with the denser elements sinking to the center by gravity, but by the gravity that the mass makes for itself, right, from Newton's law of gravitational traction. But in the differentiation, it develops this frozen crust, this solidified crust on the surface. And as is kind of alluded to in this picture on the right-hand side, it develops some kind of nascent system of plate tectonics on the surface. And so plate tectonics is driven by the fact that within this molten material here, we have these solidified plates, but the turning over of the molten material is enough to drag these plates across and create locations where there are destructive boundaries, which we'll talk about, constructive boundaries, like the mid-ocean ridge in Iceland, where Ballard was diving, and also mid-ocean rift valleys, like the Kenyan Rift Valley in eastern Africa, which are present within continents. So this is all a consequence of the lifespan of the Earth where we are now. It's trying to cool down, hasn't got there. We've got it, I guess, midlife. If you look at the moon, which was carved off, the moon has no active tectonics in it. It's small. If it's small, it will cool quickly, just like an ice cube would melt quickly if you crush it. And as a result of that, it's basically solid all the way through. There is no system that is able to drive, I presume it's solid all the way through. There is no system that can drive plate tectonics on the surface now. And so we're at a particular point in the Earth's history where it's doing this, perhaps as it loses all its heat, or perhaps as we use up its heat in geothermal energy, we might make it stop. Probably not very likely. But the process by which it happens is that you have these, what were referred to in Ballard's discussion about both constructive boundaries. So this is upwelling of magma into the mid-Atlantic ridge, Iceland being one place where the mid-Atlantic ridge is actually populated, I guess, if you look on this figure down below. And as a result of the heat transport, so this is buoyant transport. So as you heat something at depth, it becomes less dense. As it becomes less dense, it becomes buoyant. As it rises, it carries up. Once it gets here, it has to go somewhere by displacing other material that's already sitting there. If this is hot material that's coming up and it's contacting cold material, and they're the same materials, then the colder material will be denser, and that will sink down and go back. And so you start setting up some kind of convection cells. And as a part of this, you have constructive plate boundaries where you're actively supplying mass to make these plates that are being pushed apart. So you're wedging them apart at something like 5 centimeters a year. I guess he said 2.5, an inch a year, right, in Iceland, of that order. And again, since the Earth is a finite size, if you're moving this plate at some rate in this direction, which is 5 centimeters a year, you have to be destroying plate at that same rate. And so the manner in which it's destroyed is that you get a buckling of the crust. If there are sediments that are present in here, then you get the Himalayas, which was discussed earlier. If there are no sediments in here, such as on the west coast of the US, in Oregon and Washington and in BC, then you have, well, I guess you do. You have the Cascades in those particular places, but that's something different. But I guess if you look at Oregon and California, then this is backwards. This would be the west, and this would be the east, right? So this would be looking south, which is an unusual way to think of it. And then that's exactly what this is. So I guess this would be Washington here, and this would be California. No, sorry, Oregon. Should know my geography. And California below it. And so if there's no material to be built up into mountains like the Himalayas, then the other thing that happens is that as this crust dives under here, then this was originally sediments in the bottom of the ocean. They picked up water from the bottom of the ocean. And as they're subducted under this crust, what happens is that the water in these crusts, as it heats up, melts, and the water rises into the previous continental crust. And so it's not that the crust itself melts as it subducts and then rises up as magma. The crust shoots off the water that boils off, doesn't really boil, but is dehydrated from the slab as it goes down. That water rises, and as that water hits the hot crust here, it melts it by adding water to it. It's the same as melting ice by adding salt. You change the chemistry of what's there, or you change the composition of it, and it becomes able to melt at a lower temperature as you add water. As you add water to that, the magma in here, which has now been melted from the country rock, rises into a chamber, and then it rises up as a volcano, and it does its thing. It either arrives on the surface nice and quietly as a basalt volcano, a bit like in Iceland, or it blows its top as it did in Tonga, which is a caldera, maybe a 5 or 6 kilometer wide volcano, which has a very big magma chamber in it, is able to sink into it and the magma come out. Just like, for instance, in the US, Crater Lake would be that, and also Yellowstone. Yellowstone is also a caldera volcano, which erupts something like 500 million years, and it's at 500,000 years, and it's at 500,001 years now, and so that's kind of. So constructive boundary, destructive boundaries, passive boundaries is where extension in the crust pulls things apart. You can imagine that if you have some crust, well, that wasn't very well drawn, and you start pulling it apart in each of these directions, then what you end up getting is it fails and the block goes down to fill up that space, and that's exactly what you're seeing there. And so on the stuff that would have been present here, this would be the new topography. This is the Rift Valley that is developed. And just like the East African Rift Valley along here in Kenya and Tanzania, you develop along here very high heat flows because the crust is perhaps thinned by being stretched, and also it allows fluids in the subsurface to be able to go in here. And so it's probably no surprise that if you look that within the crust, and we'll look at this later, that all of the action in terms of the geothermal plants are on the plate boundaries. And so this comes from Glassey's book. I think the badly drawn arrows are the direction of the plate movement, and the yellow stars are places where there are hydrothermal plants. The red dots are the ring of fire, and these are individual earthquakes that are present along these plate boundaries. And so as you go around the world, you have the geysers, you have the geothermal fields in Nevada, the geysers being the biggest hydrothermal geothermal plant in the world. You have Iceland. This is the Mid-Atlantic ridge that comes down here. You can see the political boundaries from the countries in white. So this would be Iceland on the Mid-Atlantic ridge. The rest of the Mid-Atlantic ridge is in the middle of the Atlantic Ocean. You would have, this is Europe, this may be Italy. The very first geothermal plant is Larderello in Italy, still running after the 1920s. You see geothermal plants in the East African Rift Valley, in Kenya and Tanzania and other places. I'm not quite sure what this is. This looks like the Suez Canal, so this might be Egypt, but I don't know what that is if that's the case. Hawaii, obviously a hotspot volcano. I guess we didn't really talk about hotspot volcanoes. It's possible within the ocean crust to have random magmatic plumes coming up in different locations, and that's exactly what Hawaii is. It's sitting on top of a little hotspot where it's doing all the melting. This plume is static. As the plate moves across the top of it, you have a whole bunch of Hawaiian islands. The current one that's being erupted right now is Mauna Loa, right, the main island. But there's a trail of smaller islands which have grown in the past above this plume when the plate was above them, and they're now being eroded and disappeared. So the smaller volcanic islands in Hawaii are ones that are being eroded and be returned back to the ocean, just like the one in Togo was, in that it was below the surface mainly. I'm trying to think. I think this would be where that is, right? This is here, Tonga, not Taiwan, Tonga. Toga parties. Toba was a big volcano. This is Tonga, the island of Tonga, islands of Tonga, nation of Tonga. This would be New Zealand, the Taupo volcanic zone. Greg Bignell talked about those for anyone who looked at that stuff already. This is the Cooper Basin geothermal plant in the middle of Australia, an EGS demonstration project, which is now defunct, was not successful. I have no idea what this is. This would be Papua New Guinea, I think, and the Solomon Islands. This might be Indonesia, I guess, right? I'm trying to think. This is this potentially is the Philippines. I'm trying to think what my geography is. Again, on a plate boundary. And this would be Japan. A couple of places in Japan. And yeah, this would be the boundary on China. This is Mongolia here, etc. And so on. So the point is, you see that the concentration, just by empirical evidence, is that all of these places which are hydrothermal exist only on the plate boundaries, and these are played out. So that's great. That's great if you live in San Francisco and can get your power there. If you live here, perhaps not so great. And so part of the stuff that we'll talk about is how to kind of change that imbalance. And changing that imbalance is maybe by two things. It's maybe by this concept of deep geothermal energy using enhanced geothermal, if it can ever work. The resource is huge. And I guess the other way to take care of using geothermal and expanding its penetration to the marketplace is what we talked about in the Sankey diagram, right? As you go in the Sankey diagram for production of oil, natural gas, coal, wind, hydro, geothermal, nuclear, and to the right-hand side you go to uses and fugitive energy. So the fugitive energy was about half of the energy that was produced, and so if you can use some of that fugitive energy to be able to recover heat, that's one way to be able to by conservation to be able to fill out the energy portfolio. But the other one is by shallow geothermal heat pumps, right? So if you use the earth, the shallow earth, as a source of heat in the wintertime and a sink for heat in the summertime, then you can use that energy to be able to recover, to be able to be useful. So those are perhaps the two big solutions to our subsurface geothermal issue. So what else do we need to know about this? Well, a few other interesting facts, I suppose. We talked about the amount of the two sources of heat, one being from the core, which is 40% of the heat, some being from the radioactive decay within the mantle, this circulating magma. When it comes onto the surface, it becomes lava, but it's in the subsurface, it's magma. And if you look at these 60-40 proportions, the total is something of the order of 47 terawatts per year. Again, a useful number, right? We think that the energy use of humans on the surface is something of the order of 10 to 15 terawatts. So that gives you a rough idea of how much heat is being produced, 3 times as much, not very much actually. You'd think there'd be a huge amount coming from the subsurface. And if you divide that 47 terawatts across the complete surface of the globe, including the liquid surface, which is 2/3, then you end up with something like 100 megawatts per square meter. So that's another good number to keep in check. So something like 100, did I say mega? 100 milliwatts. So this is 10 to the minus 3. So this is 10 to the minus 1 watts per meter squared. And so that's an interesting number to look at as well, just because the relative magnitude of that. The other thing, I guess I can't do that. I'll do this. I didn't bring this to your attention for. This is, you see on the top, it's 1.1, 0 or 0.1. This is just, I can't remember where, for the life of me, where this came from. But it's a use to be able to talk about individual units. This is useful for you. Exa, 10 to the 18. Peta, 10 to the 15. So I guess I was wrong. Tera is 10 to the 12, not 10 to the 15. And you can look at global resources. What's interesting about this was these two figures at the end. A whole bunch of interesting facts. You should have a look at this. These two figures. And so these figures are things that divide power divided by area. So if you have power output for a blast furnace, power plant stack, the city of Boston was in here somewhere, I thought. Well, the country of Belgium was. I thought Boston was in here, perhaps not. How much a supermarket is. Since this is looking at the area over which that energy is dissipated, big power plant, you can work out the area of that and how much the power output would be. 1 gigawatt would be reasonable for a single power. Then these lines that go up through this diagram are in the energy density, watts per square meter. And so we just talked about the energy density of the Earth being something like 92 milliwatts per square meter. That turns out to be about 0.1 watts per square meter. And you can see where that sits in terms of other things that might exist on a single. Why doesn't it want to draw this? See the line that goes through there. And so everything to the left of here has an energy density that's much larger than that. Anything on the right of here is an energy density that's less than that. Most of the human uses are more than the geothermal output. I guess that kind of makes sense in some respects, although I'm really quite surprised that the energy output, power output of the Earth is, within a factor of 3 of what humans use. I thought that it would be much larger than what humans use, and it's not. And the same data are supplied on this. So I think this is an interesting way to start thinking about it. So energy density for the crust is something of the order of 0.1 of a watt per square meter. Again, a useful number to think about as we try and get a grasp on all these individual components. So we know something about the Earth. We know that we have liquid components, magma, in the interior and the lower and upper mantle. This is the outer part of the core. if you look at the heat fluxes across the planet, then this would be our average heat flux, right? This would be, I guess our average heat flux would be, what did we say? 92. So this is the bottom range of it. This is the top range of it. So these are the parts which are warmer than the average. These are parts which are much warmer than the average. And most of the continental crust, at each of the stuff coming across the surface, is actually quite cool. And it's quite cool because these are continents that are sitting here, and the heat has to conduct through the continents, and the crust on the oceans is pretty thin, and it has to conduct through it, but it's relatively thin, and so therefore can get through more quickly at a higher rate. And of course, the places where the plate boundaries are are very thin because they are destructive plate boundaries or constructive plate boundaries down the middle of the Atlantic, then these are places where the heat flux is really much larger than the average. And so it'd be great if you could have your power plants here. There aren't very many places where you can do that. You can do it in Iceland. It would be great if you can have your power plants here. Again, there aren't too many places. This looks like Baja, Mexico right here. So I guess this would be the geysers and San Francisco right there. And so sitting next to these zones where you have high thermal output gives you a chance to be able to get high heat flows. Some magnitudes of heat release by different elements. I'm not sure it really matters very much for us. Perhaps we're interested in the big picture. This might be a big picture of what the crust looks like. And so this would be the center of a continent where the height of this is quite high, 70 kilometers of that order. This is as you go towards the ocean. It's thinner, and it gets progressively thinner as you go around. You see the scale bar here. And depending on how much heat is conducted across here, how much heat is generated from the actual interior material, then the location of the 300 centigrade isotherm will change elevation. So you have a lot of heat generation in the material, then this isotherm will be high. And if it's high, then that means it's relatively close to the surface, which is perhaps useful if you want to tap it somehow. And in places where the heat production from the middle crust is lower, then not surprisingly, the depth to this 300 degrees isotherm is much deeper. So where are we? If you look at the US, this is a map by Dave Blackwell, and make that a little larger. You can see the outline of the states. It kind of echoes what we've talked about before. High heat flow on the destructive boundary that runs here, subduction zone. There's a subduction zone that goes underneath Oregon and Washington and British Columbia. There is a stalled subduction zone, which is the San Andreas Fault, which goes along the length of California. So strike-slip fault is that originally California was undercut by a portion of the crust, which is exactly what it does up here in Oregon and Washington. But what happened is that this crust is locked, and instead it's trying to move laterally in this direction. And so, as you know, the San Andreas is a fault that's doing this rather than doing this. And so this is the reason for this plate boundary here. So what else do you see? You see this relatively cold region. This is San Joaquin Valley, which is sediments and also the depression, if you like, between the front ranges and the Sierras. Sierra, of course, in California would be granites that have risen to make Yosemite. Crater Lake would be here within Oregon, in the back of here. And then all the volcanoes along this chain would be Rainier at Seattle, Hood, Baker, St. Helens, Shasta in Northern California, etc. So the one thing that you have going on here is that you have this collision going on. And so not only do you have favorable temperatures quite shallow, I don't know what depth these temperatures, these are heat flow rates, so these aren't temperatures. This is heat flow rates, so high heat flow is red, low heat flow is blue. So you have high heat flow rates here, But if you want to be able to recover that economically, you need to be able to have a heat transfer fluid go into the subsurface to be able to pull stuff out. And so if you don't have this material fractured so you can do that, then you have hot rock, but you aren't able to harvest it any meaningful way. The other region that's commercially viable in the US is in Nevada, the Walker Lane site. We'll talk about some of those. I think Jim Folds talks about it in his talk recorded last year. Some anomalous regions. If we zoom in, well, all of the eastern US is pretty cold, low heat flux, except for a few regions. I don't know why Allegheny College is so hot here. Looks like it is. And this also will have someone come, Patrick Fulton will come to class and talk about the Cornell geothermal project. There's a small anomaly right above Ithaca here, apparently. And everything else is relatively cold here on the East Coast. But of course, if you're able to go down 4 kilometers or 6 kilometers, then this is a surface heat flux, and you can get down to much larger temperatures as you go down. The Caribbean here, plate boundaries and high heat flows in the Caribbean. Central America also close to a plate boundary and high heat flows there as well. Why is it not responding? Okay, all right, what else? So, at least there's some rationale to what these magnitudes would be. And these are, I guess, the ones that we talked about in terms of magnitudes. The average was of this order. And so we're way, way, way below this. We're probably half of that where we are. The average values are what the heat flow is in the geysers in the western US, etc. So, what kinds of heat flows do we get? I'm not going to talk about too much of this. Oh, we're at 1 hour. I'm going to finish quite soon. Well, if you look within the crust, the lithosphere is solid. And so we said these two boundaries here at 410 and 660 kilometers are places where the composition of the mantle changes by the phase diagrams for the different minerals that are present. If you look at the thickness of the crust, which we said is about 70 kilometers, then it's not even as deep as this line here, right? It's much less than that. And so in the crust, it's solid. We can only get conduction occurring within the crust. And below the crust, we potentially get convection. And so if you look at just understanding the mechanisms of how these work, conduction is by conduction of heat. No material moves, but you just get the individual quanta of heat being carried within by atomistic transport. You certainly would have seen whoever teaches heat and mass transfer, Derek Hall now maybe, I'm not sure who would have done it in your career. Then Fourier's law is something that relates the heat flux to a thermal conductivity and a gradient of temperature. Temperature change with depth. And so physically what that represents is a column that has a lower temperature on the bottom, a higher temperature on the bottom, lower temperature on the top. So there's a change in temperature. It occurs over some length, which is delta Z, and the heat flow that comes out is a function of that. I guess the units of this would be watts per Kelvin per meter. This is the units of lambda, which is thermal conductivity. And so watts per Kelvin per meter times Kelvin and divided by meters gives a heat flux. This is going to be, you can do the math yourself, this is watts per meter squared, right? This meter here gets augmented by this meter here, and this is the watts per square meter that we've been talking about. If you want to know the amount of watts that comes out of a given area, you just multiply this by whatever that area is, and you can figure out exactly what the heat recovered is. And so if we know what magnitudes of thermal conductivities are, they're typically in the range of single digits, maybe between 1 and 10 watts per meter per degree Kelvin. So order of magnitude. It looks like these are anything between 1 and 10. Looks like the thermal conductivity of water is about half of 1.5 roughly. This is about 0.5. All these other minerals are around 5, so a factor of 10 different, right? And so rough order of magnitudes. They don't change very much with temperature. They change a little bit, but not very much. And so these might be some interesting numbers for us to keep our eyes on as we go through this class. So again, in terms of thinking about the mechanisms by which this occurs, is that conduction is much less efficient than convection. Convection is much more efficient is because it's physically moving the hot rock from one place low in the crust or low within the mantle to higher up by the physical motion of that packet of hot magma. And so if you look at what's going on in the crust, then the crust, if you look at the difference between convection and conduction, if you have conduction occurring, then it would be some temperature on the bottom, it would be a lower temperature on the top, given by this green line, and the difference between them would be given by this linear gradient, which is kind of conforming to this. It's Fourier's law. Low temperature on the surface, high temperature at depth, then there has to be a linear gradient between, a constant gradient, a linear distribution of temperature with depth as you go down. If this is a solid, then that has to be. If this becomes a liquid that's between it, then not only can it move it by conduction, but it can also overturn. So the hot stuff at the bottom, which is less dense because it's hot, can buoy up to the top. The stuff at the top is cold and dense, and so it'll want to return down, and so it sets up a convection cell. I guess I'm drawing it backwards. So the convection cell is that it takes the hot liquid at the bottom, it's less dense, it rises in the middle. Once it gets to the top, it cools down by this surface here. It's continuously being displaced by warmer fluid coming up, and therefore it falls off to the side, becomes cold, and goes down. So the net consequence of that is that if you looked at the thermal gradient across this, it would look almost like this. It would have the temperature at the base would be this. The temperature at the top would still be this, because these are boundary conditions that we're applying. Say if this is 4 kilometers deep, no, let's not do 4 kilometers because we said the crust is solid. If this is 100 kilometers deep and it's 50 degrees centigrade per kilometer, that would be 5 times 100, which would be 500 times 0, 5,000. So this would be 5,000 Kelvin. I guess that was a number that came up, roughly. The 273 doesn't make any difference. And I guess this would be 273 Kelvin, right? Or 283, whatever. But these are boundary condition temperatures that we have. So this is 273, this is 5,000. If it's solid, then the only way that you can get heat through there is by conduction. It has to be linear because of Fourier's law. If you make this a liquid, then it can move, and it's by far the most effective way of heat transfer, is that the hot fluid rises. It's hot here. As it travels up here, it stays hot, and so it arrives here at the same temperature, and it's this temperature here. It gets pushed across the side by the other fluid that's coming after it, so it goes to this point here, and then once it's here, it goes back down here. So if you think about this is not really a Carnot cycle, but it's a cycle of temperature change where you're rising things up by buoyancy, getting that heat at the surface, changing that heat at the surface by cooling, because this is the surface of the Earth, it's the boundary condition, it cools down and then gets returned. And so anywhere that we see this vertical gradient or zero gradient, this is zero gradient with depth, is where you have a very efficient heat transfer. So this is not a plate boundary, this is actually the temperature as we're going down within the crust. Anywhere where you look at the temperature being constant with depth, so the temperature here is 5,000, it's a little bit larger here, I guess, but not much. This is convection is occurring. This here is conduction that's occurring. And so we can get that occurring within the mantle, but since we're only working in the crust, maybe the deepest drill hole is 10 kilometers, the crust is 70 kilometers deep, and therefore we're definitely restricted to the lithosphere. We're not going anywhere other than that. So we can't rely on anything but conduction to be able to move fluid, except that we can use injection of water, right? There's no reason that we couldn't take a hot bead pack of sand, realize that it's high temperature, it will be conducting heat across that bead pack. If we then put cold water in on the right-hand side and withdraw that water off at the left-hand side, it will get hotter as it goes across it, just like heat going across a radiator in a car, and then you'll recover hot water at the other side. So we can think about convection in two ways. Convection in the mantle, below the lithosphere, where it's magma that's overturning to do that. Or we can think about forced convection in the crust, where we break open the crust, we make lots of cracks, we push in cold water where it's hot, we push it across the crust to allow it to pick up that heat off the hot crust and then recover it from the surface. Just like what we were alluding to, if you like, by this diagram on the right-hand side here. And so what we might want to do is we might want to make a reservoir which is very permeable. We're able to push in cold water, and even though the rocks themselves aren't convecting, the rocks are already hot, and we can force water across them. That is forced convection. Free convection is when you heat up something, boil a pot in your house, and the warm water rises and it bubbles and overturns, just like in the mantle. And forced convection is where you drive it across here by having a higher pressure on this side than on this side, and therefore you drive it across from one side to the other. So that's it. That's all I wanted to say today, I think, as we get through here. How are we doing? Are we still alive? Good.